In this class, we will be dealing with the second part of nuclear fusion. We have already seen what nuclear fusion is. It is a process of combination of two lighter nuclei to produce a heavy nucleus. In the process, a large amount of energy is also released. And fusion is known to be present in stars, and the source of energy of the stars is essentially nuclear fusion. We have seen that in sun or in stars we have two types of fusion reactions. One is PP, proton-proton fusion reaction, and CN, the carbon-nitrogen type of fusion reaction. And fusion is essentially thermonuclear in nature. So what is meant by thermonuclear? You require some sort of a temperature or a heat. Thermo means heat, right? Okay. So why you require heat in nuclear fusion? The average kinetic energy to overcome Coulomb's repulsion between two hydrogen nuclei is 1 MeV. So why we require temperature or a heat is simply because your nuclei will be repelled by the Coulomb's force of repulsion. To overcome this Coulomb's repulsion and to bring this nuclei together to form or to generate fusion, you have to have some sort of a kinetic energy. You should give some sort of a kinetic energy to the nuclei. So to impart kinetic energy, the first thing which comes to your mind is some sort of a particle accelerators. You can accelerate your positively charged nuclei so that they will gain very huge velocity and will come and strike each other to produce fusion. But in this process, you will always have energy loss due to scattering. So that means your fusion will not be sustainable. Sustainable in the sense the fusion will not be continued. Okay, because the particles will be losing energy and you cannot have a sustained, continued fusion process. So what we do is we will be taking the fuel for fusion. For example, if you are using two hydrogen nuclei to fuse, you will be taking the mixture of hydrogen nuclei and will keep this mixture of hydrogen nuclei in very high temperature. What temperature? So the temperature is calculated in such a way that as you see, the average kinetic energy to overcome Coulomb's repulsion is 1 MeV. So what is the temperature equivalent to this energy? You know the relation kinetic and average kinetic energy is equal to kT, where K is Boltzmann constant, so you will get a temperature. So if you calculate the temperature corresponding to that 1 MeV, it comes out to be 10 raised to 10 Kelvin. So if you keep the mixture of, if you keep the hydrogen nuclei in this 10 raised to 10 Kelvin temperature, it is possible that we can have a sustained or a sustainable fusion, because this at a high temperature will impart sufficient kinetic energy to have sustainable fusion process. So that is why fusion is called thermonuclear. To have fusion possible, you require very high temperature, very high temperature, and it is called thermonuclear in nature. Now, when you are giving a very high temperature to a gas or anything, you will end up in a state called plasma. So, at very high temperatures, what happens is collisions and all cause atoms and molecules to lose electrons. Okay, so they will become ions and electrons. Okay, so we will say that matter is ionized. That's a very trivial thing. When you increase temperature at a particular temperature, ionization happens, and matter will exist in the ionized state. So if the temperature is huge, we will be calling that high temperature ionized state as a plasma state, that is the fourth state of matter. That is fully ionized neutral mixture of ions and electrons, which is called a plasma. Fully ionized means there will not be any neutral particles inside the mixture, but the mixture will be neutral. What is meant by the mixture is neutral? Whatever number of positive charges are there in the mixture, equivalent number of negative charges will be available in the mixture. That is what is meant by the neutral mixture. It doesn't mean that there will be neutral particles inside. Okay, so plasma is essentially charged particles, but they will be neutral in a collective way. They will be neutral. So if you look onto the distribution of particles in that plasma, that is if you look onto that, that is essentially a Maxwellian distribution. So that means this is this curve on the right side shows you a Maxwell-Boltzmann distribution, where you have particle energy is having a range. You have different particles with different energies. If you look onto the left side of this figure, here you have a huge number of particles. Here in the y-axis you have the number of particles, and the x-axis you have the particle energy or temperature. So when the energy is less, at this area of the curve, you will have more number of particles. Okay, so less energy particles are more and high energy particles are less. Okay, so the curve is like this. So high energy particles are less. So this curve is for a particular average temperature. That does not mean that all the particles have got the same temperature or same energy. So there are particles with lesser energy and particles with the higher energy. So these particles with higher energy, which are lesser in number, are responsible for nuclear fusion. Actually, high energy particles with enough energy to permit fusion is on the right side of this curve. Okay, so that is actually the observed this thing. Some particles have energies greater than the average kT, and they actually cause fusion. So this is the area where fusion is happening in nature. So if you look onto the reaction rate of fusion, so this curve is actually the Maxwellian, which we have seen in the previous slide, the Maxwellian. And you have also another parameter known as reaction cross section. Okay, so what is the probability of reaction, nuclear reaction or nuclear fusion? That is this curve. That is called the cross section or reaction probability. So if you look onto the reaction probability, the curve tells you that particles with only higher energies have got some sort of a reaction cross section. This area you don't have any cross section, any probability for nuclear reaction. This area the cross section starts when the energy increases, the cross section or the probability also increases. Okay, so we take actually reaction rate we take as it is the product of number of nuclei and the reaction probability or the cross section. So you take these two curves, the reaction probability and the number of particles. Okay, and you multiply these two curves, the left side curve and the right side curve, and then you will get this dotted line curve. Okay, and this dotted line curve is actually the product of this curve and this curve, and this is actually the reaction rate. And by the geometry of the figure, you know that at this point, this is the point of intersection of the number curve and the cross section or the reaction probability curve, and at this point the reaction rate will be maximum because the product will be maximum at this point. Okay, so that is about the reaction rate. The reaction rate is not same for all particle energies There is a preferable particle energy, preferable nuclear energy at which the reaction rate is or the fusion rate is maximum. Okay, so keeping this thing in mind, let us have an idea about thermonuclear reaction on Earth. I already told you that the nuclear fusion is the source of energy in the stellar interior, or the star energy is essentially the fusion energy. Okay, and if you are thinking about thermonuclear reaction on Earth, why are we thinking about the fusion reaction on Earth? We know that the energy needs are day by day increasing. We are spending energy day by day in a very extensive way. You know, you are driving your cars, you are using electricity. In whatever activity you do, there are some sort of energy spending involved. And the primary fuels which we use today for energy generation is petroleum or biofuels, coal, etc. But these biofuels are expected to be draining out in the near future. And some studies tell you that biofuels, the deposit of biofuels will be fully extracted in a half century or so. From 50 or 60 years from now, you cannot depend on the biofuels. And also, you know that this problem of pollution, carbon dioxide emission, carbon budget, etc., this greenhouse gases, global warming, etc., they are actually the main culprit is the biofuels, the emission from the biofuels. So you cannot depend biofuels in future as a dependable, as a reliable energy source. So, and that is why now people are talking about solar energy. Solar energy is now widely used, somewhat widely used, but there are a lot of technology issues like you require the sunlight all the time, otherwise in the night you will not be getting the solar energy. But so you have to use the solar energy in the night. Is the energy which you are going to use in the night is actually the stored energy. Whatever solar energy you get in the daytime, that should be stored somewhere and should be utilized in the night time. So that will be a lot of technological issues involved there. Storage is a problem. It is non-reliable, as I told you. It depends very much on the sunlight, and the rainy days and all will be having problems. And cost is a very serious issue. The establishment cost, the storage cost, etc. for the solar cells is very large, so that you cannot afford. Of course, researches are going on so that solar energy may be a reliable energy source in future, but at present it is not. So nuclear energy seems to be an alternative. Of course, we have a lot of nuclear reactors. A lot of controversies are also going on. That's all. We will just forget about that. Let us concentrate on science. So nuclear energy seems to be an alternative. There is no doubt in that. Because it is available. It's once it is established, it is available. And there are a lot of good things about nuclear energy also, which we will not be discussing in a very extensive way in this lecture. But nuclear energy, you know that there are two types of nuclear energy possible. One is fission or fusion. Fission and fusion. Okay, fission also already we have seen. A lot of fission reactors are already in place, but fusion reactors are not realized even today. So what is the difference between fission and fusion in terms of energy production? Fusion is more energy efficient in contrast with the fission. You know that the fission produced for the typical fission reaction we have discussed is uranium and neutron. Uranium fission reaction. Okay, uranium fission reaction. When the uranium is bombarded with the neutron, it splits up into two, and along with that, a lot of energy is produced. Around 200 MeV of energy is produced. The typical fusion, you know that the hydrogen fusion will produce 20 MeV or 24 MeV of energy. So you may feel that 200 MeV is greater than 24 MeV, so that fission is better than fusion. It is not like that, because you got 200 MeV of energy from uranium. Uranium is a heavy element with 235 mass. Okay. So using a 235 mass fuel, you go 200 MeV, whereas fusion you are using hydrogen only, whose mass is only your 1 unit. If you are using 2 hydrogen atoms or 3-4 hydrogen atoms, it's a matter of 2 or 4 units of masses, and from that you are generating 24 MeV. So if you are just calculating the energy per kilogram, fusion is generating 10 raised to 14 joule per kilogram, and your fusion will be generating 10 raised to 13 joule per kilogram. So there is a difference of around 10, factor of 10 between fission and fusion is more energy efficient. And compared to fission, fusion does not produce much nuclear waste. Nuclear waste means the radioactive things which are produced in the process. Fission, you will have a lot of nuclear fission. If you perform fission, it is observed that you will have a lot of radioactive elements produced in the process, and that can be a nuclear waste. But fusion does not produce that much radioactive waste. So in that way, it is a clean energy compared to fusion. Is a clean energy when compared to fission, especially in the aspect of nuclear waste. And another thing is that the main criticism regarding fission reactor is that its safety concerns. It can be exploded at any time. If something is gone beyond control, the fission reactors may end up in collapse. Okay, explosion of the reactor may happen. So, but fusion, it's always in control, in the sense to produce fusion, as I already told you, you have to bring two heavy nuclei, two lighter nuclei together. That is a very serious and a very difficult process, because this nuclei has got Coulomb's repulsion by themselves. So to start fusion, you have to impose fusion. Actually, you have to bring them together. If you do not want, you do nothing, fusion will not be happening. If you wanted to start fusion, you have to you have to do the difficult job of bringing them together. So fusion is always in control. If you are sitting idle, fusion will not happen. So fusion fusion requires something to be done to be sustainable. So it's always in control because it's always in control. But the problem is problem of fusion to be produced, to be happening on Earth is it is thermonuclear in nature. We have already seen that you require a large amount of energy, you require a large amount of heat to start fusion. That much energy is not so possible, not so feasible on the surface of Earth. We cannot produce that heavy temperature, that huge temperature in a controlled way on the surface of the Earth, or that process is very difficult. But there are certain other techniques in which you can have we can have fusion. In Sun, this high temperature and high nuclear density, at that temperature we have got a very high temperature in Sun, and you have got high nuclear density. So in that temperature fusion is possible, and that condition fusion is possible, but it's not so in Earth. And stellar energy sources like PP cycle and CN cycle are not feasible on Earth because they are extremely slow. That is again another process, because another constraint, because Sun and the other stars, you can have larger number of protons and helium, whatever nuclear fuel is there, but the time taken for one particular reaction may be very large. That means that reaction is extremely slow. But those slow reactions we cannot use on Earth because we want immediate energy, so we cannot use those slow reactions on Earth. And if you look onto the fusion on the surface of the Earth, these are the candidates. Fusion involving deuterium or tritium are better candidates on Earth, not the protons. So in Sun you have proton-proton cycle. Here we are dealing with the deuterium and tritium, the isotopes of the hydrogen are better candidates for fusion on Earth. So these are the possible fusion reactions on the surface of the Earth. Here we have listed 4 reactions, 1, 2, 3, 4, and 1 and 2 are DD. DD means deuterium. 2 deuterium are under fusion process in a 2 different way. Here 1s2 plus 1s2 giving you helium 3 plus 1 neutron and this much amount of energy. So this is deuterium fusion. Another deuterium fusion is also possible, that is 2 deuterons, deuterium combined together to form a tritium. This is tritium actually, 1s3, and another proton plus 4 MeV. So these are the 2 ways in which deuterium fuse with another deuterium to form energy. Okay, 2 types of deuterium reaction, DD reaction we will call it as. And the third reaction is DT, deuterium-tritium reaction. Deuterium-tritium, that is one deuterium is fusing with one tritium, the isotope of hydrogen, and you are getting helium and some 17.59 MeV of energy. So it seems this is much better because here it is only 3 or 4 MeV of energy. Here it is almost 18 MeV of energy. And the fourth reaction we are dealing with, we can deal with on Earth is 1s2 plus 2He3. That is helium 3. This is deuterium actually, deuterium and helium, and it produces helium 4 and 18 MeV of energy. So these are the 4 type of fusion reactions which are possible on Earth. But all these reactions are not very easy. Actually, the 2 deuterium reactions, 1 and 2 DD reactions are almost possible. And the third reaction, DT uses tritium. Okay, tritium is not readily available on the surface of the Earth. It is available on oceans. So extract is a difficult process. But this is not you cannot discard this relation. We will be using this type of fusion also. But compared to the other compared to DD, this is not so easy, but it is done. Okay. So these 2 are easy reactions, but its energy is less. Okay, energy is 3.27 and 4.03, whereas this produces 17.59 MeV of energy, but requires tritium. Extraction of tritium from oceans is not so feasible, but there are some processes in which we can use this relation also. This is the most effective relation you can see. In the sense it produces 18.3 MeV, but you are spending only 5 masses, 3 plus 2, right? 5 masses. Okay, you are here, it is 3 plus 3, 6 masses you are using. Okay, whereas this is this also have 5 masses, this also have 5 masses, 3 plus 2 and 3 plus 2, but this produces 17.59, this produces 18.3. so using 3 plus 2, 5 masses, both produce energy, but this produce more energy. So deuterium helium-3 is most energy efficient, we can say, but the problem is helium-3 is not available on the surface of the earth. Helium-3 is not available on the surface of the earth. In the recent Chandrayaan and all, one of the aims, one of the objectives of the mission was to search for helium-3. So helium-3 is present on the surface of the moon, but it is very rare on the surface of the earth. If we can extract helium-3 from moon, we can bring it over here and can be used in this particular fusion. It is not an easy task to bring something from moon here, but one of the future possibilities is that extract helium-3 from moon and to bring here and to have this particular fusion reaction. So out of these 4 reactions, first 3 are somewhat possible, the first 2 are somewhat possible. The third one is because it requires tritium, it is not so easy, but it is in some way it is used. We will see it in the next slides how it is employed. And deuterium reactions can be used effectively, used on the surface of the earth, and it produces, this relation produces actually 2 into 10 raised to 14 joule per kilogram on an average. I am talking about the first 2 reactions, deuterium. And deuterium is abundant. 1 in 7,000 hydrogen atoms on the surface of Earth is deuterium. It is not so rare. So if you take 7,000 hydrogen atoms, one of them will be deuterium. Easy extraction methods are available for deuterium from ocean water, and hence deuterium qualifies as a future fusion fuel. And these 1 and 2 relations or DD reactions can be used as a fusion source or the energy source due to fusion on Earth. And this is actually, if you have got 2 type of relations, DD and DT. DD reaction, deuterium, and DT means deuterium-tritium. So this curve is actually fusion cross-section or the reaction probability, okay, probability of reaction versus neutron energy. So both DT, deuterium-tritium reaction, and deuterium reaction, both uses deuterium. Okay, so this x-axis you have neutron energy or deuterium energy, and y-axis you have the possibility or the probability of the relation. You can see that this deuterium-tritium has got more probability at a particular neutron, say 10 raised to 2. You have a neutron with a 10 square keV, and if you look on this DT reaction has got less probability than DT reaction. So for a particular energy of neutron, the DT reaction is more probable than DD reaction. Okay, so that is what this curve tells you. So when you talk about fusion on Earth, your ultimate aim is to build a fusion reactor. Like the fission reactor we have already in place, you have a lot of fission reactors. Atomic reactors are all fission reactors. Whatever atomic reactors we are referring to, they are all fission reactors. Atomic fission is nuclear fission is utilized. So our ultimate aim when we are discussing fusion on Earth is to build a fusion reactor. So what are the things in fusion reactor? It is a controlled fusion. Fusion is already controlled, but you have to have some sort of a control methods applied. It's already controlled, but you have to have some sort of a control to decide its output and decides its rate, etc., etc. And you require 3 major conditions to be satisfied to build a fusion reactor. So what are those 3 conditions? So we have already discussed these conditions. The first condition is high temperature, because fusion is thermonuclear in nature, no? So you require high temperature. See this temperature of neutron is around it happens only about 10 keV, or about 9 keV, whatever it is, 9 keV only you can have some sort of a probability. So whatever reaction, deuterium tritium or deuterium deuterium, you require some sort of a minimum energy. So this DT have got lesser energy, so the reaction probability for DT is more, and also it happens at a lesser deuterium energy. Okay, so so this high temperature is a requirement. The temperature requirement is 100 to 1000 keV. Deuterons have more reaction cross section. Okay, from the previous figure. For this area, if your deuteron is having energy in this area, you will have more reaction probabilities for both the reactions. Okay, so that is one condition. It must have high temperature and you will have high reaction probabilities. And already we have seen another requirement is you will have sufficient number of nuclei. That is called high density of nuclei. High number density of nuclei is also needed. Number of collisions must be large in a given time. Then only the fusion will be sustainable, right? So not only high temperature, but you require a high density of density of nuclei at a place to have an effective fusion reactor. Then the condition for self-sustainability. There are two conditions to have self-sustainability. Sustainability means reliable and continuous operation of the fusion process. Nuclei should stand time till the fusion takes place. That is actually the confinement problem. You know that at high temperature, these plasma particles or the nuclei are not sitting idle. They are in movement, they are in motion, no? So to have fusion reaction, they will be brought together. Okay, so for a sufficient amount of time, a sufficient minimum length of time, two nuclei should be close enough. So that is what is called confinement. So nuclei should stand time till the fusion takes place. So fusion will be taking place, but these nuclei should be there in a closed environment for a sufficient amount of time, and that is called the confinement issues. Then the second is system should deliver more energy than what is spent or lost. So we have already seen that to have fusion, you have to bring two nuclei together. So for bringing them together, you have to spend energy because you have to fight against the Coulomb's force of repulsion. So you are spending energy to extract energy. No, you are spending energy to effect fusion. When your fusion is effective, you will be extracting energy from fusion. So you are giving energy and getting energy. So there should be always, I mean, it must be in a way that the energy you get must be greater than the energy you spend. Okay, otherwise it is of no use. The second aspect is the loss aspect. There will be lot of loss of energy from the environment. So the total loss or the total energy spent, that is the energy spent on bringing the nuclei together, and the loss in the system should be less than the energy produced in fusion. So that is, system should deliver more energy than what is spent or lost. So then only fusion reactors are possible. So these are the three conditions. High temperature environment must be there, high density of nuclei must be present, and self-sustainability issues. There are two issues in connection with that. One is the confinement, the plasma must be confined, and the other is the actually the efficiency, that is more energy should be produced than what is spent or lost. Okay. So that means there is some critical conditions to be maintained in the plasma, in the fusion plasma. So one such critical condition is critical ignition temperature. So it is related to this sustainability actually. See, for self-sustainability, energy released in fusion must be greater than the energy required to maintain the temperature. We have already discussed that. Energy released in fusion must be greater than the energy required to maintain the temperature. And also there will be radiation loss in the system. And wherever there is a temperature or a heat, there will be some radiation loss, that is called a Bremsstrahlung radiation. So that is actually produced due to deceleration of charged particles. You have got this charged particles nuclei in a very fast environment. Sometimes there will be deceleration. So when these charged particles are decelerating, you will have a radiation loss in the form of Bremsstrahlung radiation. So these two things are there. One is the energy required to maintain the temperature, and other is the loss. Okay. So in the curve here, in the graph here, I have just plotted the loss. This is the loss. This straight line curve is the loss. See, both rate of production of fusion energy, and rate of loss of radiation increase with temperature. If you plot a graph, so here with the temperature here, and here you have the energy, you are plotting energy in the y-axis, and this curve is this straight line actually is the radiation loss, which increases with the temperature. Okay, and the other two curves are, one is for DT reaction and another is for DD reaction, and it is actually the energy production rate. Okay, it's actually energy production rate. So this is the energy production rate of the DT reaction, and this is the energy production rate of the DD reaction. Okay, DD reaction. And this point, say at this point of intersection, actually this is the loss. The loss after this point, this energy production rate is greater than the loss. Okay, so this can be called as a critical temperature. So this temperature, say 5 keV, is the temperature for DT reaction, below this temperature the loss is more than the energy produced, whereas above which this energy produced is greater than the loss. So this is if you are using DT reaction, then you should be using an energy of neutrons. If you are using DT reaction, the energy of neutrons must be greater than 5 keV. Below 5 keV, loss is greater. So that is called that there is a critical ignition temperature, actually critical ignition temperature. For DD reaction, if you look onto DD reaction, this critical ignition temperature is around 40 keV. Okay, 40 keV. So below 40 keV the loss is more, and above 40 keV the loss is less than the rate of production of heat in the DD reaction. Okay, so that is the concept of critical ignition temperature, above which rate of production overtakes the rate of loss. So for DD and DT we have just shown the critical temperature, critical ignition temperature, above which the rate of production of energy is greater than the loss which is already in place. So that is one criterion, one thing. Another criterion is called the Lawson criterion. Okay, Lawson criterion. So again, for sustainability we have the confinement issue. The plasma confinement time must be sufficiently long. I told you already, plasma confinement time must be sufficiently long, and also there should be higher density of plasma, that is plasma density should also be large. So Lawson criterion proposes a minimum value for the product of the two. If you take the plasma confinement time, there should be a minimum plasma confinement time and there should be a minimum plasma density. We will just see, but Lawson tells you that this product NT must have a minimum value. Okay, N and T must have a minimum value. So NT must have a critical value, should be greater than a critical value, and this critical value is depending on the reaction cross section and energy produced, etc. Okay, so for each reaction this critical value will be different. For example, see this NT must be greater than 10 raised to 22 second per meter cube. Actually it is N into T. N is in per meter cube and T is in second, that is if this unit comes second per meter cube. So ND must be greater than 10 raised to 22 S per meter cube for DD reaction, and it must be greater than 10 raised to 20 S per meter cube for DT reaction. Okay, so these are the two criterions. One is the critical ignition temperature and other is the Lawson criterion. And if you look on to the DT reaction, see this DT reaction has got lesser NT, no? This critical value is lesser for 10, this is 10 raised to 20 and this is 10 raised to 22. Okay, so DT has got lesser value of ND, critical value of ND. Okay, similarly your DT has got less value of for critical ignition temperature. Okay, so that means your DT is better than DD. Okay, your DT reaction is will be better than DD in that sense. You have lower critical temperature for DT and you have got lower NT value, critical NT value as per Lawson criterion for DT. So, but the problem is you cannot have an easy DT because of the tritium extraction issue. Okay, I already told that tritium is not easy to extract, but in other terms DT is better because it has got lower ignition temperature and it has got lower critical value for NT. But so I told you tritium extraction is an issue, but DT relation is better, DT reaction is better. So there is a one way for that, tritium is not readily available and to be extracted, but there is another way of extracting tritium, that is using lithium. So this is the relation. This is actually the first relation we have already discussed, DT relation. 1h2 plus 1h3 giving you 2He4 plus 1 neutron and 17.59 MeV of energy. That is the third relation we have already discussed, third equation. And here 1 neutron is produced, right? So if that 1 neutron strikes on a lithium 6, it produces tritium, okay, along with alpha particle helium. Okay, so if you just start this tritium DT process, this is actually DT process, and 1 neutron is present, and if that 1 neutron is used to bombard on a lithium 6, it produces tritium. Okay, so once this process starts, then it is like just like feeder reaction. Okay, the tritium fission is happening here. 1 neutron is produced, and that 1 neutron goes and hits on a lithium, produces tritium again. So it is just like feeder reactor, right? The fuel 1H3 is produced. Okay, and on each fusion of 1H3 or the tritium, a neutron is produced. A neutron is used to hit on lithium to produce tritium. So it is the fuel is regenerated. So this reaction is possible. So once the DT starts, the neutron produced will be used to produce tritium from lithium. So if you have a deuterium tritium plasma covered in a lithium envelope, so that lithium may regenerate tritium, and this reaction is possible. So fuel is generated automatically, and this is called sometimes we have the concept of breeder reactor. So this is some sort of a breeder action in fusion. Okay, so that's all regarding the fusion reactors. Now we will come to plasma confinement issues. So we have been discussing quite a long time that plasma confinement is a serious issue. So what is plasma confinement? You have to have your fusing nuclei in a particular place for a considerable length of time, otherwise fusion will not be happening. So you have to make the fusing nuclei available in a closed environment for a long time. So that is what is called the plasma confinement. So the problem is in the plasma state is already a high temperature state. Okay, very huge temperature, 10⁻⁻10 Kelvin or so. So no vessels can handle it, because all vessels will melt. You cannot melt. All vessels will melt. So you cannot have a container to enclose this particular plasma. And another problem is, if you are taking it in a container, so suppose you are finding out you have just invented a material which have very high melting point than the plasma temperature, then also there will be an issue. Plasma will lose heat by striking on walls. Okay, when there is a wall, plasma will go and strike on that walls, and there will be scattering losses, energy losses, and fusion not possible. So there must be some other confinement methods. So what are the possible confinement methods for plasma on Earth? There are 3 categories of confinement methods. One is called pinch confinement or pinch method. Other is magnetic confinement, and the third one is the inertial confinement. So let us just see each of those confinement problems in a very short way, in a nutshell. Okay. So what is pinch confinement? So this picture explains what is pinch confinement. So you are applying very high current, say approximately 10⁻⁶ ampere or greater, is passed through a DD or DT mixture, deuterium or tritium mixture. We are passing very high current. So suppose this is the place where you are just applying a current. So you are applying an electric field. So there will be these orange lines are all currents. So whenever there are currents, there will be magnetic fields around that. Okay, you know that wherever there is a current passing, you will be having some sort of a magnetic field around that. Okay, so this conduction of current is possible at high temperature, simply because the plasma is in the ionized state. So ionized state will carry current, will conduct current. So there will be conduction currents as indicated by this orange arrow, and circulating that there will be the corresponding magnetic field. Wherever there is a current, a magnetic field is there. So here the environment is, you have the electric field and the current, and you have the magnetic field and the charged particles of the plasma. So with high current, this magnetic field will apply pressure. Okay. Now how the plasma particles will move? The plasma particles, wherever there is a magnetic field, a charged particles will be trying to assemble around the magnetic field. you know, the cyclotron motion and all. So wherever a magnetic field is formed, these charged particles will be trying to assemble, or they will be producing some sort of a cyclotron motion around the magnetic field lines. So when the intensity of the current is increased, the magnetic field is also increased, and that means those particles will be applied pressure. Magnetic fields apply pressure and binds plasma to the axis. So that effect is what is called a pinch effect. If you apply current, when the current is larger, you will be having larger magnetic field, and those larger magnetic field lines will be applying pressure to the plasma particles like this, and this plasma will be confined to a very short area. So this is where it is narrowed down to a very small area where the fusion can happen. So at sufficient pressure and compression, fusion starts. So pinch effect is nothing but you are applying a current to a plasma, so that these currents will produce magnetic field around that. That magnetic field will be compressing the plasma, and they will be narrowing down the free area of the plasma, and finally when they are narrowed down to very close environment, fusion will happen. So this is called pinch confinement, but the process is very unstable. This is not used nowadays. Unstable plasma method not much successful also, because there will be a lot of leakages, because plasma particles will not be confined as we think. There will be leakages. They will not be coming to this narrow restricted region. So that is one problem. It is not so used, pinch confinement. Now the second confinement we have mentioned is magnetic confinement. Magnetic confinement uses magnetic field to confine plasma, and this is the earliest successful plasma confinement. Even now, even today, we are using plasma confinement using magnetic fields. Uses strong magnetic fields to confine plasma. There are two methods of magnetic confinement. One is magnetic bottle, and the other is toroidal confinement. Toroidal confinement, we call it otherwise as stellarator. Okay. So let us see what is magnetic bottle. So here, this is the concept. This figure is actually the concept of magnetic bottle. Here you must first of all think that these two lines, these two straight lines, it's not a container. It is not a container or anything. Okay, because no container. It's only it's a imaginary lines. Okay, you have just an imaginary line. There is no container here. You just not confused. And you have these coils like your spring. You have a spring, right? So spring, you are not winding the spring on anything. The spring, you just imagine a spring. So that is the idea. So these are some field coils through which the currents can be passed, and the coil density, the number density of the coil is more at the ends. So here there are more number of coils per centimeter than the middle portion. So that means the principle of solenoid and all. Whenever a current is passing through a coil, you will have the magnetic field, and if the number of turns is more, you will have higher magnetic field. So this is the magnetic field curve. Okay, at the two ends you have larger number of coils, so that you have higher magnetic field when current is passed, and at this point you will have this area, you will have a steady standard constant magnetic field. And this arrangement is called a magnetic bottle, because this high magnetic field is a hindrance to plasma motion. Okay, so let us see how it happens. See here, these are the field coils, these wound field coils, and these are the field lines. You know that inside a coil, the field will be straight line like this. Here there is larger magnetic field, larger number of turns, so the magnetic field have a deformed shape and a high magnetic field. Okay, high magnetic field, but will have a dissimilar magnetic field than the central portion. Okay, so what is the principle? Current through field coils produce strong magnetic field. So this current through the field coils produce strong magnetic fields. At the ends, the number of turns is more, and hence more magnetic field. Here you have a more magnetic field. Magnetic field is stronger. Okay. The plasma particles undergo helical motion around the field lines. I already told you, whenever there is a magnetic field line like this, the plasma particle will be just revolving around this particular field line, and it will be a helical motion, because there will be a velocity component, and because of that velocity component, that will be if there is a field line, the particle will be undergoing a helical motion like this. Okay, but when it comes to one end, there it finds a very huge magnetic field. Okay, so there the particle cannot penetrate. The particle cannot go further. So it comes back. So this helical motion, if it goes to the right side, when it finds this higher magnetic field, the helical motion now turns to the left side. So it's an oscillatory motion like this. It cannot go beyond these high magnetic field points. So the plasma is trapped inside the two higher magnetic field, stronger magnetic field points, and that is why the term magnetic bottle comes. So the plasma particles undergo helical motion around the field lines, and they are reflected back and forth at the stronger end fields, and these end fields are sometimes called the magnetic mirrors, okay, because they are reflecting at this point, and plasma will be trapped and confined. So this is the arrangement of magnetic bottle. Okay. Now there is another confinement that is called the toroidal confinement. Okay. So what is toroidal confinement? That is this is the shape of a donut, or this is actually a toroid, torus, or whatever it is. Okay. And this type of, again, this is not a vessel. These coils are there. These are the coils. These are the field coils are there, but there is no enclosure. Okay, the enclosure is just shown for clarity. Okay, what happens is there is a toroidal coil carrying currents produce magnetic field lines parallel to the circumference of the toroidal tube. Okay, so this toroidal tube, the imaginary toroidal tube, these field coils, when you send current through these coils, magnetic field will be, these dotted lines actually represent the magnetic field, dotted lines. Okay, so currents are actually shown with the arrow mark. They are just curling around the toroidal shape like this. Okay, and so this is the field lines. These dotted lines are the field lines, and if plasma is here, the plasma will be encircling these field lines in the helical motion. Okay, so plasma confined in helical motion along the field lines. But the problem is field will be stronger inside and weaker radially out. So that is a problem of the toroid. You will have stronger field inside. Here you will have stronger field, and outside you will have lesser field. That's because of some sort of a geometry of the figure. Here you will have weaker field, and at this end, inner side, you will have stronger field. So there will be a non-uniform magnetic field actually. Okay, field is not uniform. So that means there will be drift for the particles. Okay, the particles will have a drift from the lower to higher field, or from the higher to lower field. Whatever way they are drifting, the particles will be nearing the boundaries. Here there is a boundary, and here there is a boundary. Okay, so if the particles are encountering non-uniform magnetic field, there will be a drift from lower to higher magnetic field, or higher to lower magnetic field, whatever it is. So whatever ways they go, they will be reaching the boundary, and there will be a tendency for the particle leakage. Okay, so to compensate for that leakage, we have just modified the geometry. So this is a geometry again. The right side we have shown another geometry. So here what is happening is, whatever is happening in the right lobe or the right toroid, the opposite things will be happening in the left toroid. Okay, so if one particle is going to the outer section, there is a tendency to go to the outer radius in the right lobe. There will be, that particle will be having a tendency to go to the inner side of the this left lobe. Okay, so I will explain. I will just tell once again. So if a particle is experiencing an outward drift, means it is just going to leak from this side. A particle is experiencing an outward drift in this particular lobe. Opposite things will happen in the left lobe. That is, that particle will be having an inward push, not an outward drift, but an inward push in the left lobe. So that drift tendency is nullified when it completes one complete helical motion. So that is this geometry. The geometry as in the second figure nullifies this leakage. The two lobes are having opposite magnetic environment. So whatever leakage tendency is there in this lobe will be compensated that will be nullified in the left lobe. That is this geometry, and this toroidal confinement is also called stellarator. Okay, and another toroidal confinement is called tokamak. Tokamak is actually a Russian name. Actually, this idea was proposed and realized by Russians, and tokamak is the Russian abbreviation for toroidal chamber with the axial magnetic field. Toroidal chamber with the axial magnetic field. So this is actually a toroidal chamber, but there is one thing is that here there are two fields. That's actually a modified toroidal magnetic field. Okay. Actually, here you have got this type of a magnetic field. This is called toroidal magnetic field. That dotted lines represent magnetic field. So in the tokamak, that magnetic field is already there. This line, that is called a toroidal magnetic field. Okay, toroidal magnetic field. This magnetic field. And in addition to that, there is a poloidal magnetic field. Poloidal magnetic field is just like, so you see the coils here. So instead of coils, you just imagine magnetic field. So if these two lines are magnetic field, these dotted lines are magnetic field, these field coils, they are actually current coils here, but I assume them to be magnetic field. So these two magnetic fields are there. So that is what is shown here. There is one magnetic field in this way and another magnetic field in this way. So this is toroidal magnetic field, this is toroidal magnetic field, this circle, and this etc. are poloidal magnetic field. So combination of two magnetic fields is applied to the plasma, and plasma will have an helical motion inside that. That helical motion is shown here, and that helical motion is actually confined to the center of this toroid. That means the leakage problem will be nullified. The plasma will not be going to the sides, will not be going to the boundaries. The plasma will be confined to the center of the toroid. So that is the effect of this poloidal magnetic field. Okay, this poloidal magnetic field just encircles. If this is a magnetic field, with this poloidal magnetic field just encircles the poloid so that the particle cannot escape to the boundary. So these two magnetic fields used together is actually tokamak. This okay. So this path of confined plasma is helical. Here the poloidal magnetic field is produced by a current induced in the plasma. That is another thing. Toroid, we know how it is produced. Toroid magnetic field is as in the previous picture. But this poloidal magnetic field is induced. That is this magnetic field. This magnetic field. Okay, is induced by a current in the plasma. You will be inducing a current in the plasma, and that current will produce this magnetic field. And that is the idea of toroidal confinement using tokamak. So tokamak is a very revolutionary idea in the many fusion experiments and in a very fusion laboratories. Nowadays we are using tokamak for plasma confinement. We have one plasma laboratory in Ahmedabad in India, that is Institute for Plasma Research, where we have a tokamak, and one fusion reactor is being just designed for the first time. The fusion reactor is not realized so far, but it is being designed. It is being it is just in the phase of making out. So we are just constructing a fusion reactor in France, and that is called ITER, International Thermonuclear Experimental Reactor, fusion reactor, ITER, International Thermonuclear Experimental Reactor. So in that ITER also we are using this tokamak for plasma confinement. That nuclear fusion reactor is not realized even today. It will take another 5 to 10 years to be operational, ITER to be operational. And another confinement, the third confinement we have to discuss is inertial confinement. Inertial confinement is a different process. It is not neither magnetic nor electric, no magnetic field or current is used. Instead, the technique is very simple. Deuterium tritium pellets are produced. It is not radius of 0.1 millimeter. Deuterium tritium pellets with a radius of 0.1 millimeter are heated and compressed. They are heated and compressed using high power laser beam or electron or ion beams. Using laser beam or electron beams, we are just heating deuterium tritium pellets of very small radius of 0.1 millimeter, and they are being compressed. When they are compressed beyond a particular value, implosion is an inward explosion. Okay, inward expansion. So there is an explosion like thing. Explosion is always outward and implosion is inward. And when there is an implosion, the temperature rises to the critical ignition value. That means fusion requires a critical ignition temperature. So when these deuterium tritium pellets are compressed using this high power laser also, at one time implosion takes place and the temperature rises to minus 10 raised to 10 Kelvin or so, which is a critical ignition value, and fusion takes place in a very short time. Okay, a series of such pellets, if ignited in succession one after the other, then you can get a supply of steady stream of fusion energy. So this is inertial confinement process. Okay, so I think we have just discussed the second part of the nuclear fusion almost in detail, and fusion reactors are not a reality even today, but in the coming future, I think we can hope that fusion reactors will come into place and will replace the fission reactors already in place. So that completes this lecture. Thank you.